Okay, so this is I'm going to work through this problem that was in the notes for today. So a wheel is slowly turning at 1 radian per second when an outside force causes the angular velocity to increase to 4 radians per second. If it takes 5 full revolutions of the wheel to reach its final angular velocity, what is the angular acceleration provided by the force? Okay. So when starting with rotational motion questions, usually it's the best to just label the variables or list the variables that you know, and then try to figure out what motion equation is sort of the equivalent of that. Meaning, if I had those variables in a linear system like D and A and V, what formula would I use to solve it? And then all you got to just use the same formula, but you're just going to use it with rotational variables. So let me show you how that works. It says it's initially turning at 1 radian per second, which means we have an omega I, and that is 1.0 radians per second. Okay, so we're given omega I. It says its angular velocity increases to 4, so that means we're also given an omega f. It takes 5 full revolutions, so 5 full revolutions is 5 full turns. Now the question is, what variable is that? 5 revolutions is an angular distance. It's 5 full turns. And so we are actually being given theta. 5 revolutions is 5 times 2 pi radians. So that is 10 pi. And it says that we're trying to figure out the angular acceleration, so alpha. Right? So these are the things that we're given. Now, in a linear system, what variables would these be? Well, omega I would be VI, omega F would be VF, theta would be D, and alpha would be A. And so now you can see that if you had all these 3 variables and you were looking for A, the formula would just be the VF squared formula. This is the formula you would use to try to get A, right? That's what you would do. We're going to do the exact same thing, but in a rotational setting. So it's going to be omega F squared equals omega I squared plus 2 alpha theta. Remember that the part of this unit is knowing what units or what variables sort of correspond to a rotational setting here. So this is the formula we're going to use, and we're solving for alpha. So omega F squared minus omega I squared all over 2 theta has to be alpha. And now we can just plug in our numbers. We'll say that 4 squared minus 1 squared all over 2 times 10 pi has to equal our alpha. And now I wish I had my calculator ready. Oh, there it is. So it's going to be, looks like 15 divided by 20 pi. So what is that, 3/4 of a pi? Or, sorry, let's just do this. So it's going to be 15 divided by 20 times 3.1415. And it looks like 0.239. 0.239 radians per second squared. Remember, it's a angular acceleration, so it's radians per second squared. Just like meters per second squared would have been a linear acceleration. Okay. So that is how we would solve this one. Now let's go to the next problem in the PowerPoint, which is this sort of helicopter-y problem. So here, helicopter blade accelerates at 35.5 radians per second squared. If the initial angular velocity of the blade was 5 radians per second, how long will it take for the blades to complete 150 turns? Okay, so let's just do the same type of thing. Let's list the variables that we're given. We are given the angular acceleration to be 35.5 radians per second squared. It says that the initial, not final. Oh, goodness. Goodness gracious. Okay, so let's try this again. It says that the omega F is, and I just did the exact same mistake again. Sorry, guys. The omega I is 5 radians per second. And it's saying how long will it take to complete 150 turns. So we know that the theta, the angular distance, is 1,500 turns, which is 1,500 times 2 pi. And we're trying to figure out the time. How long does it take? So the next thing we do is sort of convert this into a linear system, just to figure out what we're talking about. It's not like we're actually going to solve it linearly. We're just trying to figure out what formula is the best one. So we were given a sort of the equivalent of, why am I insisting on going VF? I don't know. We're the equivalent of VI. We are given D, and we're looking for T. Okay, so already I bet you that you know what formula. If we were doing this, we would be looking for the distance formula. So dF equals di plus vit plus 1/2 at squared. All right, in a linear system, that's what it would be. So guess what? It's the same thing in a rotational system. It's going to be theta f equals theta I plus omega it plus 1/2 alpha t squared. And now all we're going to do is solve. So theta f, it's 1,500 turns. So this is going to be 1,500 times 2 pi. And that's going to equal, now this right here, the initial was 0, hadn't been turning yet. Or at least we're not interested in what had turned before the problem started. We're just, okay, so from the minute the problem starts, how many turns? And that's why we're going to set that as 0. And the initial was 5, and we don't know the t. And 1/2, and now the alpha is 35.5, and then t squared. So you can see already this is going to be a quadratic. I'm not going to solve it all the way through. So this is going to be, let me just set this thing up. So it's going to be 35.5 divided by 2, 17.75. So 17.75 t squared plus 5t minus, so 3,000 times pi, 9424.5 equals 0. And so here is, this is a 17. Here's your A term, 17. Here's your B term, here's your C term. So you can plug this into a quad solver now and you can get your time. And then, so we don't know what the time is, but I can set you up for the solution for the next part. If it takes an angular velocity of 2,000 radians per second to achieve liftoff, how many seconds will that take? I'm going to do this in green just to separate it. So in this case, the omega f is 2,000 radians per second. And we're trying to figure out the time it takes to get liftoff. Well, the original angular velocity was 5, and the acceleration was 35.5. Now you can see that this is really the equivalent of, I'm going to do this up here. That's the equivalent of this, so this is going to be like that. We're solving for t. So omega f minus omega I all over alpha equals t. And here we're going to have 2,000 minus 5 all over 35.5 equals t. And so that's that one I can solve. I don't have to pull up my quad solver. 56.2 seconds. And that's how we do these problems.